Good morning, everybody. Welcome to the webinar. We're just waiting for participants to trickle in and we'll start at 8:03. Good morning, everyone. Welcome to the webinar. We're going to start in 1 minute now. Okay, good morning, everyone. Welcome to the Research Coordination Network webinar on SARS-CoV-2 and wastewater. This webinar is for junior researchers, meaning postdoc students and early career professors to present on their research related to SARS-CoV-2 and wastewater. I want to thank everybody for attending and thank everyone for their hard work and service to the pandemic, which seems to be going on longer than we all hoped. Today, we are really gracious to our two speakers. We have Juan Eduardo Sosa Hernández, who's a postdoc at Tecnológico de Monterrey in Mexico. And then he will speak first. And then after that is Kyle Curtis, who is at Hampton Roads Sanitation District, a scientist there. So we will go ahead and kick off. Eduardo, do you want to go ahead and share your screen? Oh, before we begin, one more note for all the participants, a reminder that to please put your questions in the Q&A, and then you can upvote questions that you want the moderator to ask. And we are not able to monitor the chat. So if you put your question in the chat, please don't do that. Please put it in the Q&A. Okay, thanks. Go ahead, Eduardo. Thank you.
Thank you, Ali, and thank you all the network to organize this event. I will give you my presentation about the first glance of WBE applied to Tec de Monterrey campuses against SARS-CoV-2 outbreak and early warning tool to protect the community. And I will show you a study case. And well, this work has been done with a great collaboration with Arizona State University, with Professor Rob Halden and his team, and from our side at Tec de Monterrey, with the leadership of Roberto Parra Saldivar and our big team now. So first, I will talk to you about what we have here in Monterrey and what is Tecnológico de Monterrey. Tecnológico de Monterrey is one of the biggest private schools in Mexico. I'm not afraid to say that it's the bigger, and it has a wide coverage over all the country. It has 38 locations, and within locations we have 26 campuses and 10 high school little campuses, can we say. Our population, well, our president is David Garza, and we have a very large population within these campuses. Obviously, there are differences between each location, but in general, or the average population, it's around 10,000 people each campus. And well, here are some data that I won't describe, but is there if you want to check it later. And here I send you a map of Mexico, where you can see all these blue dots represent one of these campuses. In some locations, there are more than one campus to cover all the demand that comes here. Some examples of this is Mexico City, where in that area we have 2 big campuses, and the distance between those are in some miles. Here I present you the main campus, that is Monterrey campus. This is where we are located. And as you can see, it's a very big complex of buildings. It covers all these 3 main blocks and has some presence in different other locations. And well, what we got at the beginning of this project is this capacity to apply this wastewater-based epidemiology to all these campuses. And prior to this, we have been monitoring the pandemics in the Monterrey metropolitan area. Again, thanks to the collaboration with Arizona State University. So at the beginning, we only have the possibility to apply this to this private school, this technology, and the previous knowledge and the strong collaboration with Arizona, and especially with Professor Ron. It is good to tell you that we started this collaboration in 2018 with a project that was funded by GCSO. This is the project, and we were a big consortium with 4 universities and in 4 different countries. It included obviously Arizona and Tec de Monterrey, and also King's College London with Ron Halden, and Dublin City University with Fiona Riga. Within this collaboration, we also used some urban metabolisms in general to explore the activities in the 4 different cities in these countries. So this is what we had at the beginning. We had the knowledge, we had some data that we started taking from Monterrey City from April in 2020. So with this, we made a pitch with the directors of Tec de Monterrey, and they accepted or wanted to participate and to implement this on Tec de Monterrey. So at the beginning, we need to cover these 38 locations. So we started some personal training. We had several meetings with them, and this was a challenge because we were in the distance, and these new tools, we had to make the material for them to watch some videos, some pictures, some manuals, and well, we succeed on that, and we managed to give these training courses to these people that were going to take the samples in each location and be prepared. So here are some pictures of the training courses, and then there are some pictures of the people wearing the PPE and taking the samples as we taught them. Here there is Chiapas, León, and Monterrey. Still, we have many pictures we can share later. With the collaboration and with some studies, we develop and adapt this risk level stoplight to ponderate and to weight the RNA quantification per liter for the samples that we got. And with these two main things, we started a protocol according to the CDC guidelines and complementing with our stoplight system to generate a response protocol. Well, this was at the beginning, and we didn't have any laboratories or any infrastructures to run the samples at our locations. So we started this project by sending the samples from each campus in all the states to Monterrey and make a big batch. And with this batch, we sent to Arizona State University, where Professor Halden and Dr. Erin Driver will analyze the sample. At the beginning, in September, we started with a small portion of the campuses, 18, still some big numbers to consider with the logistics and the sample handling. And we were sending the samples to ASU. And this had some challenges. The first challenge was the transit time. It was the samples to be processed, taken and processed took almost 10 to 12 days, and we got the results. But the main thing is that we have some advantage since the outbreaks developed within this period of time. So we still have some opportunity to have the information on time and to have valuable options for the decision takers that were the leaders of each campuses. So we were able to have funding to establish our laboratory. Obviously, with the pandemics, everything got slower. So we were planning to have the laboratory up and running by December, late December, but it was a challenge too. And we got this up to all the way up to February 1st. So at this point, I was trying to look for people to integrate in our team. So we found some very good professionals in the area. Here are their pictures. This is Dr. Manuel, Dr. Aelda, Dr. Parra, obviously the leader, Dr. Mariel, and the Bachelor Sofia. With this team, we are managing these 20 campuses. Actually, we have this capacity, but we haven't implemented in all the spaces. We have trained 86 people to have this sampling, and we developed this protocol and this information flow chart where we can do all the process, and along with the health services in each campus, we deploy the tracing contact and the searching of the individual that has the COVID-19. So here it is the study case. I can tell you first that the Tec has some guidelines for safe reopening or safe ingress into the campus's facilities. So some of this stuff is 10-day quarantine, a questionnaire, some temperature checkpoint, disinfection venue. And well, even with all of this, you know, we have asymptomatic people or people that is developing the illness in this stage. So this is the actual data from a study case. In the first two lines, you can see a federal stoplight quantification that let us know if we can reopen or come back to activities. Then there is a state report, and then our general sample. We have these sewer networks, and we know how it is distributed in every campus. We know all the buildings, and we know when we need to take samples from there. So in this first stage, we were very restricted capacities in this campus, and we were green in all this time from September to October 30. In October 30, we got a positive signal. We deployed the protocols and found that some people was infected. We followed the health instructions and came back to the activities. We continued 3 weeks, and then we started a pilot to see our capacities, if we have the opportunity to follow in more details, more buildings. We were able, obviously, and then from this point to December, when we got the winter break, we stopped it and then came back, and we continued with the pilot. And at this stage, the federal stoplight was red, and it happened in the campus. In more buildings, we got positive cases. Again, we triggered the protocols and followed the traceabilities, and we spotted where the people was infected. And we could continue in some other spaces as normal, as usual. And with this information, we have been able to develop a startup. That's the logo here, Martech. And we are trying to get in touch with companies or with municipalities. Actually, we are now trying to establish a standardized protocol for Mexico City within several labs and several institutions. This includes the UNAM and the IPN and the Polytechnic Institute. Well, you all know the benefits and this stuff, how this can really make a change as an early warning if you have the baseline with no positive cases. And there is a link where we have a video of this laboratory. And I would like to share another screen where we have established a dashboard to collect all the information. Still, we have some pending stuff to continue with the collaboration with the health departments and to ease the information flow. But in general, as you can see within this dashboard, we have some information about different campuses and how this has been implemented there, and then the relation with the positive data and the individual sampling and processing of information for each campus and each building. Well, I think I'm over the time, and I think we can go to the questions and answers, right?
Great, thank you, Eduardo. That was really informative and interesting to see the buildup of the whole process. So just as a reminder for folks that maybe came in just a minute late or forgot, please enter any questions you might have for Eduardo. There's a little Q&A box and you can enter it there. And even if you don't have a question, this is a location where you can upvote the questions to make sure that we get to the ones that might be of most interest to you. So the first question that we had there, and I was wondering this myself. So you have these different risk interpretation thresholds, you know, essentially going from green to red and their orders of magnitude. And I think that this is something that a lot of us in this field have been struggling with, interpretation of this data, simplified interpretation of this data, especially to communicate to public health professionals and decision makers. So how did you come up with these thresholds and how are they, I'll add a little bit to this question, how have they been received by decision makers on the other hand as well?
Well, this stoplight or this different threshold were based in general on the quantification of the individual shading or quantification of the feces. And well, we know, everybody in this field knows that this is a challenge. This is not the standard delivery of each individual. It varies or has different quantity over the population. But well, at the beginning, this is an opportunity to improve. We are trying to find some other controls. Actually, in the project with Mexico City, we are struggling with that a little bit because we want to have representative data according to the population. And well, still we don't have the a good answer for that part, but the decision maker have accepted and have adopted this information very good in the means that we try to have a baseline that is green, so nobody in the campus should be infected. And once we have this information with this positive campus, we can track down some people that was entering to the campus, and sometimes it is people that is asymptomatic. We have some of those cases in very particular areas. And some of our advice is to keep the population living and doing all the activities in the building that they are supposed to visit, and not wandering around the campus. So this makes easier for us to correlate this information along with the flow data, no, for the sample. Even though we don't have auto samplers, so we do this by personnel, and still we don't have a good measuring of the flow. It is a challenge that we need to address too.
Yeah, great, thank you. That kind of leads into the next question, and I'm going to combine a few of these questions here. So it was asked, you know, if you could specify whether these were grab samples, and then I'll follow on to that a little bit. How did you select where and when, if they are grab samples, to collect them? And then also there was a related question. Once the samples have been taken, how were they processed and preserved prior to or after shipping? What was your process like there?
Yes, we usually do the sampling on Mondays. So every Mondays we try to do this sampling. Those are grab samples, but we do 2 grab samples in the morning. It should be around in the morning from 9 to 11 a.m. Lately, to the more probability for the people to go to use the service. No? So later for shipment and everything, we keep the samples at 4 degrees, 4 Celsius degrees with some ice, and we manage the logistics to pick up the sample by midday, the same Monday, and to ship directly to Monterrey. For almost all the campus, we got the samples next day morning, so it is in good shape, and we start the process in the laboratory from the, it should be the Tuesday, yeah, the Tuesday.
Great, thank you. So then the next sort of batch of questions, and I'll kind of combine these as well. First, is the dashboard that you showed available to the public, or is that internal to Monterrey or your group?
Yes, this is internal for the decision makers and the people that had some action in it. Actually, I missed this information, but we have the directors of the campus, the director of operations, and there is some human resources director that has the information, the medical lead in campus, and also some security people that has some monitoring of the people in the campus. And with all this information, this dashboard summarize the data and gives directly to the health leader, so he can follow or she can follow.
Great, and then sort of following up on that, there was a couple of questions about, you showed some links, for example, I think the one at the bottom of this slide here, maybe after, if it's possible, after you're done presenting, could you include any of those links in the chat on the Zoom? Because there was a couple of questions and interest in being able to follow and see some of those links. So yes. Thank you very much, Eduardo. That was great. And I guess in the interest of keeping us on time, we'll move on to our second presenter, Kyle Curtis from Hampton Roads Sanitation District. So please feel free to share your slides and get started, Kyle.
All right. There we go. There we go. Okay. Able to see that?
Yeah, you're all good.
Yep.
Okay, great. So thanks very much for the time, and yeah, I appreciate the opportunity to be able to do this. I've enjoyed this series, and it's cool to be able to be a speaker here now. So what I'm going to talk about is applying what I think is kind of a simple Bayesian sort of framework for understanding your wastewater surveillance results for the SARS coronavirus 2. So the good thing about talking to this group is that I'm going to have just this one bullet that says the whole context of this, everything in this talk is wastewater surveillance, and not go into the details of what that is. But just understand that I'm typically talking about treatment facility scale. So I think we're all familiar with what that is. You know, we're conducting surveillance for molecular markers of SARS-CoV-2 in wastewater. But I will make a couple points about building scale surveillance where I think some of these methods are more appropriate. I'm not going to talk about the analytical methods at all because there just isn't time, but we have a publication out that outlines those. So feel free to shoot me an email, or if you haven't already, you can talk to Raul Gonzalez. He's the collaborator on this, and he could definitely give you a good rundown. So what I am going to spend time talking about is, you know, when we get detections for the virus in wastewater, what does that actually mean? You know, could you assign a reliability or confidence to that? And kind of tied up into that question is, what's the likelihood that we're making type 1 or type 2 errors? So when do we get false positives or false negatives? And and also related, and something I think that's really important is how do we incorporate not just our test results, and maybe our analytical controls, but all the information we have into the interpretation of our results. And so that's going to be the focus of today's talk. So all of this is in the context of kind of a Bayesian reasoning, and we may be familiar with that, but I want to, for folks who aren't, I kind of want to just go through this simple made-up example to get us all in that frame of mind and point out how this can be useful for understanding things that sometimes actually are somewhat counterintuitive. And so, for the purpose of that, we have this made-up disease, and let's just say, you go to the doc and the scenario is, okay, they say, hey, I'm sorry, your test came back positive. We do think you have this disease. The test effectiveness is 95%. The false positive rate is 6%, so it's not nothing, but it's pretty low. And the disease incidence in the population is like 1 in 1,000. So you're given all of this information, and naturally you think, like how worried should you be? But to kind of frame it in terms of probability a little more, the better question is, what's the likelihood that you have the disease? And so over here, same information that I kind of just quickly threw out. This is what you have to go on. So if you had to assign a value to it to say, how worried should I be about this, or what's the likelihood that I do actually have this, what do you think it would be? And I'm not asking you to answer right now. I'm going to pop it up there in just a second, but it's kind of fun to come up with a guess in your head, because I think the result is somewhat counterintuitive. And that's how all of this is going to be. So if you put these values into a really simple probability equation that I'm going to show here in a minute, you come up with this number. So it's more like a 1.5 to less than 2% chance that you actually do have this disease given this information. And so that might not be obvious, and that's what I want to do, is show how this relates to our wastewater data and some of the same situations that can come out of this if you don't think about it in kind of a probabilistic way. And so same information up here. I want to quickly mention how this actually works. So the reason this works is really kind of hinges on the idea that, one, you have to integrate all of these pieces of information that you have, and two, you kind of just have to get your head around the idea of not just a simple probability, so something like, what's the chance that you would pull a club out of a full deck of cards, right? Not a simple probability like that, but a conditional probability. So a conditional probability is something like this second bullet. What's the probability of A given that I already know B? So to go back to the deck of cards example, you might say, what's the probability that I pull out a club given that 2 hearts have already been pulled out, right? So that changes your probability a little bit because you have less cards to deal with. And I think we probably can kind of understand that. But, to bring it back to the world of science that we all work in, our analytical tests, often we can figure out, or there is a reported sensitivity or specificity for those, right? And those are actually also conditional probabilities, whether we think about them that way or not. So the sensitivity of a test is something like, what's the probability that you'll get a positive test result given that the disease is actually there? So this is kind of sticking with that same made up example. But we're going to pivot this to SARS-CoV-2 and some of the CDC assays here in a minute. Similarly, specificity, what's the likelihood that you get a negative test result given that the disease is absent? So these are conditional probabilities right away. And then our prior is a simple probability. Our prior is going into this before we ever run any kind of test. What's our baseline guess that X event occurs? So in this case, that you may have this disease. And here we would just use the incidence, right? We would just say this is how frequently we see this in the population. So knowing nothing else, that's what we should go with. And so what we really care about here, the thing that you might have just guessed in your head on the previous slide, is also a conditional probability. It's what's the probability that you have the disease given a positive test, right? So that's kind of how this stuff works. And I'm going to show, a basic formulation of Bayes' theorem here. But what I want to do is show you how the pieces of this all fit into this equation, and then how it really boils down to something that's far simpler than it may look at first. So this is, if you Google Bayes' theorem, you're going to see something like this. Sticking with our disease and our clinical diagnostic test example, you can put these pieces in, and I won't go through each one, but if you've kind of picked up on the way I've been talking about this, a plus sign means, the presence of or positive for this, and a minus sign would just mean the absence of. And so you can take a look at how these things fit in. But once you just start plugging numbers in, you see that it's not really that tricky. So this big wordy kind of term is actually just the sensitivity that we saw, right? I use the word effectiveness, but we can certainly use sensitivity there, times the incidence, right? So this is, this is our true positive up here. And then we see the same term down here, plus all the times that we would get a false positive. Because remember, the only thing we care about here are all the possible ways we can get a positive test result. So true positive and false positive, as the denominator here, will give us this really simple equation for what's the likelihood that we have this disease given a positive test. And so to pivot over to what we're actually interested in, you can plug in some different words and get the same sort of situation. So what's the probability that SARS-CoV-2 is present in a sample given a positive analytical result or given a detection with one of the assays? I just threw N2 in there. You could put any of the CDC tests or any of your own tests in there. Any assay will work as long as you have the sensitivity and specificity information. And like I mentioned before, all of these kind of break out into a simple sort of ratio of what's the likelihood that you get a true positive over the likelihood that you get any positive at all, the sum of all the possible positive outcomes. Or even more simply, what's the probability of the event of interest over the probability of all the possible events? And so we could probably talk about it more, but with 20 minutes, I'd rather get to how this actually works in practice. And so feel free to, ask any other method questions about it afterwards. The application of this to wastewater surveillance, I think, comes in times during the pandemic or times during your surveillance when it's really important to know, but it's not immediately clear if a detection is very reliable. So, or a non-detect is very reliable. And so I've put up this plot showing kind of the progression of the pandemic in southeastern Virginia in our wastewater facilities that we've been monitoring since last March, along with the clinical cases, just as a reference to say, when we have lots of clinical cases and very high viral loads, so concentrations are very high, we're nowhere near a limit of detection, this isn't something that we spend a lot of time doing. But early in the pandemic, when we're having sporadic detections, some plants come up positive, some negative, some assays come up positive, some negative, and we're kind of hovering right around that LOD and clinical cases are low, then it actually is relevant to think like, what's the likelihood that this is a true positive or is that a true negative? And I would just add to that, I don't know when late in the pandemic is. I wrote that, but I realize that's different depending on where you are and how things shake out. But at some point when viral load and clinical cases are down, and we want to do something that's more like hotspot surveillance, so localized resurgence, maybe, again, that's where it's really important, but maybe not obvious to know, was that detection reliable or are all these non-detects reliable? And that's where you might want to assign something like this. I'm kind of hesitant to use the word confidence because that goes along with a more frequentist kind of statistic thing, but that really is what it is. How confident are you in that result? And so like I've alluded to, the math is not tricky. I know that just based on the fact that I can do it. And the pieces of information you need are also, pretty easy to come by, I think. So for the 3 CDC clinical panel assays, we found specificity reported in this publication by Liu et al. In 2020, which many of you may be familiar with. I'm going to make a comment about why these are asterisks here in a second. Sensitivity is an interesting one. We came up with a way to kind of back of the envelope get an idea of sensitivity for the purpose of doing this investigation. And so what we did was, we took our treatment facility and we went back in time and said, knowing how many clinical cases we have in the zip codes that service that catchment area, how many times did we also detect the virus, basically when we should have, and how many times, how many times did we detect the virus when we should have? And by should have, I mean, we have individuals shedding virus in the catchment, and so we should be seeing it at the plant. That's a simple way. It's likely not the only way to do it, but based on when we started doing this kind of work, that was something we were able to do. And then prior probability, if you've delved into the world of Bayesian statistics at all, people often say this is so subjective that it makes it difficult, but I actually think there's a lot of ways that you can incorporate what you know, both about recent trends in your data and trends in the clinical data in your area, and set this in a reasonable way that can give you an output that makes sense. And we'll talk about that a little bit more too. So this table does show the actual values that we used. I'm going to show results here on the next set of slides. So just know that these are the values that get plugged into the various versions of the equations and give you your likelihoods. The note about these two being 0.999 is that if you read this paper or go back and read it again, maybe, you'll see that there actually was no cross-reactivity in they compared these assays using viral isolates and I think a couple bacterial isolates, but basically other respiratory pathogens. They saw no cross-reactivity and they had an N of about 22, I think. For the purpose, so no cross-reactivity essentially gives you a specificity of 1, which kind of makes all of these equations truncate to, perfect specificity, and it becomes not very interesting to do. Based on the idea that we wanted to investigate this without kind of running into that, and also the fact that I don't know if specificity has been looked at specifically in wastewater, and it's at least reasonable, I think, to set the specificity very high, but less than 1, so that we can get a better idea of, what these curves look like without everything just pegging up to the top of the graph because specificity is perfect. Hopefully that made some sense. If you have a question about it, I'm happy to go into that a little bit more too, but that's what you'll see. And that's what we used. And so if one of the interesting ways to look at this is to just say, let's not worry about the prior right now. Let's take the assays and just take a look at the likelihood of true positive, which you have on the top, and true negative on the bottom. And just look, how does the function look all across every possible prior? So often the x-axis on the plots that I'm going to show you shows a 0 up to 1. And that's just because these are all the possible prior probabilities. A prior probability of 0.25, just to make sure we're kind of all on the same page, is saying, before we ever collect a sample, we're saying there's a 25% chance that we will detect SARS-CoV-2. And so what these are showing is if you run these assays individually, so we'll take a look at N3 because it's a little bit easier to see, at a prior of 0.25, if you get a detection, the likelihood that it's a true detection, is somewhere up here around 0.8, right? Meaning you can say, yeah, there's like an 80% chance that that's a real detection, even with a pretty low prior. And so the reason that these things go up towards 1, so posterior is the language you use, but basically the y-axis is saying, what's the likelihood that this is a, either true positive for this top panel or true negative for this bottom panel. The reason these things go up towards 1 on this one and kind of start off by 1 and dive down towards 0 on this one is that up here, as your prior probability goes up, a positive detection is just more and more reliable, right? If before you ever sampled, you said, well, I think there's a 75% chance that it's there, and then you sample and get a positive, well, that is highly reliable, right? Hopefully that makes some sense. You know, by the same token, on the bottom, if you want to look at what's the likelihood that a negative is a true negative, you can see that down here where the prior is very low, a negative is very reliable, right? And hopefully that, if I've done a good job at all of describing this, hopefully that makes sense too, because you're saying before we ever sampled, we think there's a low chance that it's there. And so if we get a negative result, there's a good chance that that's a real negative result. What I think is pretty interesting about this plot, you know, and it kind of shakes out in the way that you would think, these all three of the assays, N1, 2, and 3, the functions kind of sit right next to each other and kind of, you know, dive down towards 0 as your prior goes up, is that for priors over something like 0.75, the likelihood that you have a true negative actually goes down below 0.5. You know, if you could draw this line across, that's what you would find. And so that's kind of an interesting finding in the sense that if you have a lot of clinical cases or some other good reason to say, yeah, there's like a 75% chance that it's there, and then you get a negative, you know, you should probably think there's less than a 50% chance that that's actually a real negative. And hopefully that's something you can follow there. So something else that we did is, and this just kind of fit in with how we were monitoring for SARS-CoV-2 and wastewater and how we thought other folks were. We used a version of this equation where you look at the intersection of events. So you can find these equations in a paper that we have out and a paper that Johnson et al. Have out. But basically you can run the exact same kinds of equations for not just a single assay, but running 2 concurrently and say, all right, given the possible outcomes, you know, they both are positive, they both are negative, or they disagree, what now does our confidence that SARS-CoV-2 is present look like, right? And so one of the things that might be apparent before we even dig into what these lines mean is that if you run 2 assays instead of 1 and they agree, you know, both negative or both positive, that should be more reliable, right? And that is the case. This blue line that just kind of looks like a square where it goes immediately up to essentially 100% likelihood that SARS-CoV-2 is present, regardless of how low your prior is. Yeah, I mean, that's the one where both come up positive. That's because they're really good assays and they both agree on this finding. And so that makes sense to us. Kind of moving in a little bit, this line where you also pretty much immediately get to very high confidence, and it's hard to see because it's both sitting on top of each other, but it's when you run either N1 by itself or N2 by itself and they're positive. And so those also are highly reliable. The ones that I think are interesting are the red and the yellow lines where the assays disagree. So where you get discordant results. And so what you get here is for these, you actually have a very high confidence that SARS-CoV-2 is present, even at these very low priors, which I think is what might be counterintuitive. And so if you got these assays that are very similar and you run them and one says, oh, that was positive, and the other one says negative, you know, you may sort of intuitively think, is it something like a 50% chance that it's there? Or if it's at a time where there's many clinical cases, you might think it's that means positive, or few clinical cases, maybe that means negative. But actually, the assays are so good that if you run both and one comes up positive, you have a really good chance that it's present. So see, Allie came back on. I'm not sure how much time we got here. I don't want to run over.
Yeah, your time is up, so you should wrap up, Kyle. Thanks.
No, that's a good place to stop. The next one's a whole different thing, so I'll just stop there.
Great, thank you, Kyle. That was a really great presentation. I know that we have a few questions in the Q&A. Sure. As a reminder to anyone add your questions into the Q&A if you have any, and we'll try to get through as many as we can. So the first couple of questions here are actually sort of related. So I think sort of, I think I'm going to ask the second first, and the first one kind of builds onto it. So basically, one thing that I think a couple people noticed was in calculating sensitivity for the assays, it uses an assumption based on, if you can maybe go back to that slide with that calculation, that would be great.
Yeah.
Yeah, so cases in your catchment, right, is like a factor in determining your sensitivity. And that is going to be dependent on, right, lab confirmed case counts, how the testing, et cetera. Yeah. So one question was commenting on how you think that might be affecting your sensitivity measurement. And then in addition to that, you know, if you have, or if you know that those are underreported, or if you have a sense for what the true cases might be, you know, do you recommend any sort of multiplier on that value, or have you basically investigated that that impact of it?
Yeah, that's a good point. One of the ways that we try to make that a little bit more real, or at least not biased low, given that we know that it would be, is that we wouldn't be able to do this early in all of the pandemic, because at least where we are, and I think most places, testing was so low, testing rates were so low that you couldn't do that. And so that's just, I totally acknowledge that that's the case. As you move forward, and the data that we use for this, where testing rates were, I would say, pretty high, and definitely comparably high, what we've done, and when we use clinical cases, we kind of often do this, is we take values that we've seen reported for rates of asymptomatic cases, and we make the assumption that those won't be captured in the clinical data, because I think that is probably pretty close. And then we try to scale up our clinical cases by a value, you know, what we do it in crystal ball, where we say, like, all right, we're going to assume a uniform distribution between the lowest rate of asymptomatic that we see, you know, in the literature, and the highest. And so we take our clinical cases and scale it by values from that factor, from that, you know, distribution of asymptomatic ratio, and just try to push it back towards whatever the true value is that we won't know. Yeah.
Great, thanks.
Sure.
All right, the next question is, let's see. So in looking at the Bayesian method, your prior distribution has less impact on the posterior distribution the longer, you know, it runs, right? I guess if I'm understanding this question correctly, and the posterior distribution will converge after a certain number of runs. So can you comment on why your prior has so much impact on the posterior distribution?
Yeah, feel free to follow up, or whoever this is, to email me if I don't get this. But the way I'm understanding is that, so what we haven't done is modeled this. We're actually kind of just doing it with point estimates. And so it's not, we're working on this morning, and don't have a clear way to set a whole distribution of priors that accurately takes into account our best idea of what, you know, a prior should be. I spent too much time on the methods and didn't get to how we actually would set a wastewater prior, but what we've been doing is used kind of recent sampling. So we have a network of 9 facilities, and we've said very simply, what was the % positive in the last either 1 week or 2 weeks? You know, we can tweak that however we like, but we basically have used recent sampling to say, we're going to make a point estimate of a prior just based on the % positive, and then we're going to calculate our posteriors from that. I acknowledge that if we were doing this on a bigger scale, yes, we would continue to shift that distribution of the posterior until it converged around something. But this is frankly not that sophisticated, and meant to be more basic so that it's, you know, more accessible and easier to use. So that wasn't intentionally dancing around it. Whoever asked that question, feel free to shoot me an email, and we can get into the weeds more.
Yeah, thanks. I I was wondering a very similar thing, you know, because with the pandemic changing so much, your prior distribution, you know, if you took into account all of the previous data with so much variability, that's obviously not maybe the most appropriate starting point. And so it sounds like you're taking into account just, you know, a week or two, which sounds is similar to how clinical cases are being tracked and that sort of thing. So, all right, the next question is, how are you, so basically how you're using this information, are you using this to drive development of understanding your detection method and lower your limits of detection to improve confidence? Kind of, can you comment a little bit more on how you're using this in practice?
Yeah, so I guess the short answer for the first one is we haven't yet used this to tweak our LODs, so our analytical limits of detection for the assays that we actually use. But I mean, right now it has been largely, I don't want to say theoretical, but basically we have a similar paper out where we did this with some microbial source tracking assays. And so we kind of had the framework for how to do this. We just needed to figure out how to get, you know, these values. So I would say the main way that we would use this is probably internally as we interpret the data and pass it on to the folks that we work for. We give all of our data to our local health department, but so far this interpretation hasn't been a part of it, just because we want to very simply let them do the interpretation part. Yeah.
Sure. And then one more question that came in on the chat. So sort of the other side of the sensitivity equation you're using, right? The detections in wastewater. Have you evaluated how issues with the molecular workflow, like inhibitors or anything like that, could influence the assumed sensitivity based on your detections?
Yeah, so fortunately that work was already done and we feel good about it just on the lab side as this surveillance, I guess surveillance program kind of progressed and we realized we're really going to be doing this for a while. Raul and our analysts did a lot of work to understand the controls and the sensitivity. And so at this point, you know, I know that we certainly look at the controls each time, particularly if a sample appears to be inhibited or, you know, suppressed, but I think we feel pretty good about those detections. Yeah, when we plug them into this to get an idea of sensitivity.
Great, thanks. Unless I'm missing anything, let me look really quick. I think that was all the questions that came in and we're right about on time. So I think we'll stop there. And I want to say thank you again to both of our presenters, Kyle and Eduardo, for joining us and sharing your work today. It was a really great webinar, and for everybody else, we'll have our next webinar coming up in a couple of weeks. So thank you so much for joining us, and everybody have a great day.